So welcome to this talk about uCache, our work on a customizable unikernel-based IO cache. I'm Ilya, Masson, and this is a joint work with my colleagues at TU Munich, Masanori, Misono, Viktor, Leis, and Pramod, Bhatotia. So caching is an essential aspect of the design of data-intensive applications. Nowadays, in the cloud, there is a wide diversity of applications, including database systems or ML systems, and they all execute very different workloads and have varying requirements for the cache. On the other side, cloud environments include high-performance I/O devices, such as NVMe SSDs or InfiniBand NICs, and the performance of this device is improving at a much higher rate than other components of the servers, like the CPU or the memory. In this context, designing a cache is challenging because it has to adapt to all these use cases while delivering the performance of modern I/O devices. Now, to better understand the problem, let's delve into what the application requires from the cache. First, application may want non-hardware supported page sizes. Typical database systems use multiple of 4 kilobyte pages, such as 8 kilobyte for PostgreSQL or 16 kilobyte for MySQL. And other data processing applications may use even bigger sizes. Second is to customize the replacement policy, including the eviction, the prefetching, and they want to customize it to their workloads. In particular, cheaply preventing the eviction of a page is a fundamental requirement to ensure transactional safety. So let's just take 1 second to look into that. Take a database system with a buffer manager that manages the cache. When a query arrives, the buffer manager must ensure that the page that has been modified is not persisted until the transaction has been logged or committed. Finally, cloud database systems commonly use local and remote stores and require the cache to support this diversity of backends. So what are the options available to the applications? Traditionally, applications used OS-level caching by creating a file-backed memory map region in their address space using the mmap syscall. After that, they can simply access the data with normal load and store instructions. Internally, the OS page cache catches the misses by handling page faults in the region. This approach is very simple for the application, since the OS transparently manages the cache. However, it has two major drawbacks. First, the OS page cache, as well as the kernel I/O stacks in general, have been shown, including in some of today's presentation, to lack scalability and, in general, to add too much overhead to fully leverage these high-performance I/O devices. Moreover, the POSIX API offers little control over the cache. The transparency that was a good thing becomes a problem for applications that have an insights on their workload and want to control more precisely the cache. So as a result, most applications nowadays implement their own cache in userspace. And this offers better flexibility, and they can also leverage kernel-bypass I/O solutions like DPDK or SPDK. However, userspace caches imposes an explicit interface with pin, unpin, or acquire release to the application because they cannot rely on page faults. This makes the application more complex and pushes the cache to be specialized to a single application. So we have on one hand OS-level caching that is relatively simple and general, and explicit userspace caching, which is flexible and performant. Can we overcome these limitations? So we ask ourselves the following: can the OS provide a simple, flexible, and performant IO cache? And we propose uCache, a customizable memory-mapped IO caching framework. Our goal, as I said, are to be flexible, to adapt to these multiple workloads and storage solutions, to be simple, to let the application decide the level of control it requires, and to be performant, to enable applications to leverage these high-performance IO devices. The key idea for uCache is to leverage the unikernel architecture. And we especially use 3 advantages. First, unikernels are single address space, meaning that the OS can be completely dedicated to the application. Second, unikernels are library OSs, where the application is co-located with the kernel in kernel space. This avoids expensive syscalls and also enables the application and the kernel to have access to each other's symbols. Finally, unikernels are built into VM images that can be directly deployed onto the cloud. So uCache uses the unikernel architecture for its capabilities of co-designing the OS with the application. Let's see an overview. An application can create a memory region by calling mmap, making uCache a drop-in replacement to POSIX for existing applications. The application can then access the region with normal load and store or with explicit operations. Internally, the cache manager fills and evicts pages using replacement policies that can be customized by the application. And finally, the cache manager interacts with the storage through the IO layer, including potentially application-defined backends. Now that we have seen the overview, let's delve into the design. So, as I just said, we use the unikernel architecture for its co-design capabilities, but it does not solve all our problems. We face especially 3 challenges with uCache, namely the application OS coordination, the scalable cache operations, and the flexible IO abstraction. Let's focus on the first challenge for now. So typically, unikernels also adopt this POSIX-compatible API, which suffers from the same limitations as in traditional OSs. So as we described earlier, existing caches propose 3 different interaction models to the application. The first is to be completely transparent, with just mmap a file and then issue load and store into the region. Second is to be explicit, precisely control what operations the cache performs. And finally, there is a middle ground where the application first customizes the replacement policies and then can access the region with load and stores. So to be general, uCache must not only provide each of them, but enable a spectrum of interaction modes, leaving to the application the choice of what is the most relevant for its users. To address this challenge, we propose 2 abstractions. The first is the virtual memory area, which represents a cache region. While inspired by VM area struct of Linux, it differs by being shared between the application and the OS. The second is the buffer abstraction, which represents a page or a group of pages in a VMA. The size of the buffer is fixed at the creation of the VMA, and this buffer represents the granularity of cache operation. These shared abstractions enable the application to specify customizable policy simply by attaching function callbacks to the VMA. Compared to the POSIX API, which only exposes a virtual memory region to the application, uCache enables coordination between the OS and the application through these shared VMA and buffer abstractions. Let's now look at the second challenge. Modern hardware is highly parallel, especially CPU have a high number of cores, and on the other side, you have IO devices that also have a high number of hardware queues. However, during its operations, the cache must modify a centralized data structure, the page table. The typical solution in practice to improve the scalability of modifications to the page table is to use lock-free operations, which avoid synchronization on accesses that are separated by more than a cache line. However, high-performance caches also need to evict pages in a batch. This is because unmapping a page in the page table requires to invalidate the TLB on all the cores, which requires an expensive interprocessor interrupt. To mitigate this cost, the typical solution is to invalidate a batch of page per IPI. The challenge arises when you combine both approaches. To batch, you need to accumulate pages until you found enough candidates. And state-of-the-art approaches lock those candidates to prevent concurrent modifications, which does not hold up to our goal of lock-free operations. So how do we combine those 2 solutions? Well, to address this challenge, uCache uses optimistic cache operations, and especially we leverage our access to the page table to modify the page table entries, or PTE, in 2 steps. Let's see how it works. Starting from the initial state of a page, when it is uncached, when a thread handles a page fault, it first allocates a physical page and tries to map it to the PTE using a normal compare and swap operation. After finishing the initialization, for example, after reading into it, it can flip the present bit, which makes the page visible to the rest of the system. If a concurrent thread accesses the page when it is uncached, then it will contend to set the physical address. And if it loses the race, or if another thread accesses the page while it is being inserted, then it will just wait for the present bit to be set. Now, when a thread is evicting a page, it starts by clearing the present bit. And once it has found enough candidates, it can invalidate TLB for this batch. Then it can clear the physical address of those pages. And if another thread accesses a candidate, it will simply set the present bit again, which cancels the eviction. This also works for pages composed of multiple hardware-supported page sizes, but I encourage you to read the paper to find more details. To conclude, uCache uses optimistic operation to limit synchronization even when batching. Moving on to the third challenge. For the major part of this talk, I have focused on the case where the application accesses a storage organized with files and where caching is beneficial. However, data-intensive application can combine multiple types of accesses, including some that do not benefit from caching, or even where caching is adversarial, for example, with write-ahead logs. If we simply bypass the existing OS stacks and force the application to use our IO layer, then we have to be compatible with all these other use cases, which is undesirable. Second, application can access a wide range of IO backends, including local and remote stores. And these remote stores are typically accessed via userspace libraries, as current OS stacks do not support non-file system-based storage. In the same ideal of integrating into existing application, uCache must be able to use these application-defined IO backends. So in general, how do we enable flexible storage access to the applications? To address this challenge, uCache introduces two abstractions for the IO layer. The uVFS abstracts IO backend, or uStores, and dispatches operation at the buffer granularity to the corresponding IO stacks. We leverage, once again, the unikernel architecture to enable the application to use custom uVFS-compatible IO stacks. Our IO layer exists in parallel to the existing kernel IO stacks. To optimize the NVMe uStore, we decouple the IO path with the control path following the standard file system for compatibility, while the data path leverage a high-performance NVMe driver for maximum efficiency. To conclude, uCache enables performant and customizable IO without hindering compatibility. We implemented a prototype for uCache in the OSV unikernel. Our prototype cache manager uses the clock replacement policy by default, and we include a NVMe-optimized uStore compatible with the X4 file system. Now that we have seen the design, let's move on to the evaluation. We evaluate uCache across several research questions, but in the interest of time, I will focus on the following: the performance of individual cache operations, the performance of uCache as a drop-in replacement to mmap without customization, and the performance of uCache in the buffer manager of a database system. I encourage you to check the paper for more results. Our experimental setup using an Epic server equipped with a PCIe 5 NVMe SSD. And in our experiment, we compare uCache to OS-level caching with mmap and to specialized userspace caches. For a fair comparison, mmap and userspace caches also run in a VM. Starting with micro-benchmarks, we focus on the throughput of insertions in the cache. We investigate the performance of insertions in the out-of-memory case where it requires periodical evictions. We evaluate the scalability of uCache by varying the number of threads, and as presented in the figure, uCache outperforms mmap with improvements ranging from 2 times to 50 times. We can also see that uCache scales linearly with the number of threads. Moving on to the end-to-end performance of uCache, we compare the random lookup throughput in a region backed by mmap or by uCache. We use 200 gigabytes of data size and 64 threads, and we vary the memory quota given to the system. In this figure, we can see that uCache outperforms mmap by up to 78 times. We can also observe that uCache not only outperforms mmap by an order of magnitude, but also degrades less the performance as the memory quota tightens. To conclude, uCache is a compelling replacement to mmap in terms of performance. For our buffer manager use case, we use the VMCache, which is a state-of-the-art buffer manager. VMCache enforces transactional safety via fine-grained concurrency control, and VMCache uses an anonymous memory maps region and explicitly manages the cache using either POSIX with the madvice syscall or with the custom kernel module xmap. We port VMCache to use uCache and customize a replacement policy to respect transactional safety. We use the TPCC workload with around 1 terabyte of data and 128 gigabytes of cache size. uCache performs similarly to xmap and significantly outperforms the POSIX baseline. We also note that uCache effectively enables the buffer manager to saturate the bandwidth of the SSD. In conclusion, uCache can integrate complex application semantics without incurring overheads compared to the state-of-the-art buffer manager. To conclude, in this talk, we asked if the OS could provide a simple, flexible, and performant IO cache. To answer this, we present uCache, which aims to be convenient like OS-level caches while delivering performance and flexibility. We design uCache to provide customizable and scalable caching by leveraging the unikernel architecture. Through our evaluation, we demonstrate that uCache outperforms mmap and can be customized like specialized userspace caches. Our prototype is open source on GitHub, so please feel free to try it out. And with that, I'm open to questions.